start the recording as usual. Start the screen share. And let's see, I have lecture 4 open, example 4 open, and everybody got their homework done on time, which means we can go over the answers as a group. So I thought that that might be a good way to start things off. So I have one of your sets of answers pulled up here. No one got a perfect score on this homework. So if you're feeling bad about missing one or two, you are in good company. It's such a grad student perspective to focus on the number right versus the number wrong, right? Like how many questions were in this assignment? 48 questions and then 21 results questions, right? So if you only missed one or two, that's great. That's still doing proportionately very well. But I thought rather than have the mistakes repeat themselves, it might be good for us to go over it. So do you want me to just go through the answers, or do you want to have any specific questions to start things off?
I have a question about number 63. Yes, 63.
Let's go find that one. Next section. Ah, yes, right here. So this is from the model where you're predicting fits thrown from age. What's your question?
So I selected predicted fits thrown for 3-year-olds relative to 4-year-olds. And I guess it should have been flipped the other way.
Yes.
Why might that be the case? Is that something like obvious that I missed somewhere, or did that take a little more intuition?
I will never say that any of this is obvious. What I will say is that this is a point that I've tried to make repeatedly, and so if it's not landing, then I need to do a better job of making the point. It's all about who is the reference group. And so relative to is always the reference. And the reason that matters is that the sign of the slope then tells you which is higher, but it's relative to the reference group. So it should be 4-year-olds relative to 3-year-olds, because the intercept in this model gives you the predicted outcome for 3-year-olds because they are the group coded 0. The slope coefficient then gets you from the 3-year-olds to the 4-year-olds. And in this case, 4-year-olds throw significantly fewer fits, which is why the slope coefficient is negative. So if it were worded the other way, the slope coefficient would have to be positive to talk about how 3-year-olds differ from 4-year-olds.
Okay, that makes
better.
That makes more sense. And now that you say that, it all comes back. I wish on here I would have remembered that, but it is what it is.
You'll have more than one chance to practice, I promise. But yeah, it boils down to the intercept. So the analogy for me for the intercept, it's the you are here sign of the map of your data, right? Everything is relative to that. So in this model, the 3-year-olds are the reference point. They are the you are here. So relative to age 3, where do you go? If the slope then applies to how 4-year-olds differ from 3-year-olds, because the 4-year-olds are the group coded 1. So direction does matter.
So can I ask this again just to make sure I understand?
Sure.
In your example, let me actually just make this large screen. In the example that's on the screen, it says that the intercept, so number 62 is 6.56, and the slope estimate is negative 2.15. So based upon those two numbers, since we have the intercept, that tells us where the 3-year-olds are. The slope estimate tells us where the 4-year-olds are.
Exactly.
And because that's a negative and the 3-year-olds higher, then we would basically flip it because of the negative. So, well, I guess that's where I'm caught up. I know that those two numbers are there, and the 3-year-olds, yeah. So I guess, can you break that down from, I see this intercept and I see the slope, and I see that the slope is negative, and I know the 3 to 4-year-olds. But intuitively, my mind wants to say that, oh, because of this negative relationship, for 3-year-olds, I'm going to have less for 4-year-olds.
Okay, I'm going to break this down with paint.
Cool.
So we have, say, the 0 group, These are the 3-year-olds. Here are my 4-year-olds. Okay, so in the model, 3-year-olds are coded 0. The 4-year-olds are coded 1. So the intercept for number of fits thrown was what number? 6.56. So we'll put that, let's say like, no, make it up higher, a little higher. We'll say that 6 is right here. So the 3-year-olds throw 6 fits on average. The 4-year-olds throw about round numbers, 2 fewer, so let's make that 4. So the mean for the 4-year-olds is here. The slope is negative. So as you go from the 0 group to the 1 group, the predicted outcome goes from 6 down to 4. So the difference between the groups is the slope of 2. How's that for some paint? This is the original iPad sketch.
Yeah, got that. So back to the answers. So I do see the negative slope and everything there, and then like 3 to 4. So we would see predicted fits thrown relative to. Oh, okay. Well,
Lisa, is it it's the language of it? Is that part of it? Is that you have to say relative to the, I forget what it's called, group.
To the
So,
intercept
like,
reference group.
everything is relative to whatever the 0 value is or whatever. Is that right?
Yes, exactly. I'm
Is
frozen.
that part of the holdup?
Yeah, well, I'm getting the dreaded unstable message. Can you all hear me?
Yes.
We're okay? All right, good. Okay, so say that again, Mackenzie.
So is it the language of that question that is part of it too? Is that you have to say relative to the whatever the control group or whatever is? I'm not sure if that's okay.
Yeah,
Okay.
so predicted, so the red part here is what's wrong. The green after it is what's right. The correct answer is that the slope refers to how predicted fits for 4-year-olds relative to 3-year-olds. And it has to be that way because 4-year-olds are the lower group. That's what the slope applies to. Otherwise, we would be interpreting it backwards. So back to my drawing here. Because the 3-year-olds are coded 0, they are the reference. So the slope is negative because it's going from 0 to 1. If I recoded the data so that the 4-year-olds were the reference, then the slope would have to be positive to get from this group to that group. So it would be the same slope of 2.15 either way, the same significance test either way, but the direction. 4-year-olds are lower than 3-year-olds. And that's what the slope is telling us. It's telling us how 4-year-olds as the 1 group differ from 3-year-olds as the 0 group.
I think I just complicated that more in my mind for that answer. And I understand that. I think I was looking for a mathematical computation for some odd reason on that.
Well, the computation you would have done, so in the estimate statements that go with this, right, it would be to compute the mean for the 4-year-old group as the 1, it would be intercept 1 plus age 1. So it would be beta 0's intercept plus beta 1 for the slope gets you to what the predicted mean is for the 1 group, which is the 4-year-olds in this example. And you already have the mean for the 3-year-old group because that's what the intercept means. So some of the answers, for instance, were redundant on purpose, trying to get you to recognize that. So like the fixed intercept that you entered here is simultaneously also the predicted mean for the 3-year-olds because that's what the intercept represents. Okay, other specific questions, or would it be helpful to go through the list? Because I saw some points of common error, but not exclusively.
I think it would be helpful for me to go through each of the parts where we're putting in the words. So I think that's where, or maybe because I don't get the instant gratification of seeing the green light afterwards, but I think that's where some of the confusion lies for me.
Yeah, with a four choice alternative, the green would be way too easy to find, right? So, yes, let's do this. And yes, in the spirit of Beavis and Butthead, there's one of their episodes where he's like, words, words, words. Yeah, words matter. Words are the hard part because SAS and Stata aren't going to tell you what the numbers mean. I wish they did. My husband and I had talked about writing a software program together where his job would be to write the program and my job would be to program it to tell you what it means because it is algorithmic once you get a hold of it. And can you imagine how much that program would sell for if it told you what the answers actually meant? But that's another conversation. So the computational questions all seem to be fine for the most part. There were maybe one or two that folks missed. If you have questions on how you should have gotten the right answer, I'm happy to answer those questions, but I'm going to just go through this as if the computation parts were correct. So section 1 was an empty model. So in the empty model, all you have is a fixed intercept and a residual variance. So the fixed intercept then is your best guess as to what someone's outcome is going to be. If you don't know anything else about a person, your best guess is the mean. So the intercept estimate is the overall sample mean. I believe the choices on this, another one was population mean. I'm just going to tell you right now that is never the correct answer because the population is a hypothetical construct. The only time you really know what the population is if you made it up yourself. Like if you're doing a simulation study where you made up the data to make a point, which is what I've done a couple of times for demonstration purposes. So this is the sample mean. The other choices were, I think, for someone with 7 pleases or for a 3-year-old or for a 4-year-old, those cannot be correct at this point because those predictors aren't in the model. There is nothing in the model. The model says that everybody has the same predicted outcome, which is just the mean at this point. And then this intercept standard error, so this is reviewing vocabulary. This is one of my trickier sets of drop downs. I'm kind of perversely proud of this one. It's it's standard deviation versus standard error, and then the squared versions of those, looking for you to be able to separate those. So if I'm talking about the intercept standard error, then this answer is incorrect because it's talking about slopes. So at this point, what you're interpreting as 0.21 is the intercept standard error. So it's not talking about a slope, which is referring to a relationship. It's talking about a conditional value of an outcome. So the correct answer is right here, the average distance of a sample mean from the population mean. So the intercept in an empty model is just the sample mean. So its standard error is the same thing that you learned as the standard error of the mean a couple months ago. So it tells you on average how far off a sample mean is predicted to be from a population mean. It is a function of the standard deviation of the outcome and sample size. Confidence interval then. Confidence interval is a tricky one, but it is not a probability. It's not the probability of observing anything. It is a proportion of times that the interval is expected to contain the population value. So in this case, we're talking about the population mean and the interval around the given sample mean in reference to that. So it's the proportion of samples that are expected to contain the population value, so 95% in this case. The t-test statistic, so looking at whether or not it's positive or negative and whether it's significant or not. So the t direction tells you positive or negative. The p-value that goes with it, if it is less than 0.05, that makes it significant. And then last but not least, residual variance was estimated at 7.71. So in variance, you're in squared metric. And this is a number that describes the dispersion of cases around the sample mean. So putting that together, the correct answer is that residual variance refers to the squared average deviation from the mean of any child. And it's from the mean because in this model, the only parameter that you have is the mean. So it's not a deviation from a regression line per se, because there's no x-axis to make the line out of. You're not happy about it. Well, I'm sorry to have made you unhappy, but focus on all the ones you did get right. It's okay to be not perfect yet. That's not a reasonable goal. Okay, questions on any of those? Okay, then we go into the next one. So the next model, which would be called a simple linear regression, the word simple meaning that there's only one predictor, linear meaning that it is a linear model of a quantitative outcome for a quantitative predictor. So in this case, you had to center pleases heard at 7. So that changes the scale of the predictor so that the new 0 point is 7 pleases heard, and that becomes your intercept reference point. So the reference child then, according to this model in section 2, is a child who was heard saying please 7 times. The intercept then tells you the expected number of fits thrown for such a child. So we have the intercept estimate of 6.03. So somebody who says please 7 times was predicted to throw 6 fits. And we have the standard error confidence interval around that. The slope estimate in this case was negative. So that's the expected difference in y per additional unit x. And so the other choices had those things backed around. So it's the difference in predicted fits thrown as the outcome per additional unit of the predictor. So for every additional please heard, the child is predicted to throw 0.17 fewer fits. So being more polite in please is related to being more polite in behavior as measured by fewer fits thrown. The slope standard error then, so now we're talking about standard error as an index of inconsistency of our result across repeated samples. So the slope standard error is the average distance of a sample slope from the population slope. And it's not the squared version. So it's in the units of the original variable, so in the units of slope. So it would be squared standard error would be something called sampling variance, which is a thing but not something that we've really talked about. Okay, confidence interval, same thing as before. It's expected to contain the population value in that percent of the samples. This slope corresponded to a t-test statistic of -2. Let me go up here and find, oh, the p-value was right at 0.05 to 2 digits here. So it was significantly negative, such that people who said please more threw fewer fits. And then I asked you to calculate the number of predicted fits thrown for a couple different levels of pleases heard, plus or minus roughly a standard deviation on the variable, I think. And in the standardized solution, you can convert that slope estimate to a standardized slope, which is in z-score units. And then last but not least, relative to the previous model. So the residual variance to start with was, in this data set, 771. After adding number of pleases heard, it went, oh goodness, this one went up. 7.57 was significantly smaller. That's what was supposed to have happened. Now I'm seeing why so many of you picked that. So here's an interesting thing about, I made the effect size too small on this time. So this will be something I'm going to have to fix. Now I'm seeing what the problem is. Teachable moment. Let me pull up my slides. Here's what happened. Sums of squares. Okay, one more. Okay. So R square is actually computed using sums of squares. It's not computed using residual variance directly. And the reason for that is exactly what happened in this instance of the homework. It is theoretically possible for the variance to increase after adding a predictor because the residual sums of squares could have not decreased enough to offset the loss of 1 degree of freedom. So it's rare in practice, but it can happen. So did that happen in other folks' data where the number actually went up? And so you're like, okay. Yeah, that is a population values not chosen well enough problem on my end. What should have happened is that the residual variance should go down if you add a predictor that is significant. And the reason that it went down is because of the slope for the new predictor, because that's the only thing that differs between models. So let me go back through your answers and change them to be correct if you said it went up, and because it actually did go up based on the numeric thing, because that should not have happened. Grr. See, now I'm angry with myself for having made an error. So yes, in theory, this number should decrease.
It's okay. You got every other one right. So
Is
focusing on the good ones.
Okay, so 771, it did go down to 757 in this case. It went down a tiny bit. Did it go up in any of yours? Jens, it did. Okay. Yeah, so welcome to sampling fluctuation, by the way. So the idea of inconsistency of these results, all of you have the same population that's generating your data. The difference is in drawing one sample, what actually happened. So Jin's data wandered into the corner where the effect size was small enough that the change in sums of squares residual was not enough to offset the loss of a degree of freedom. So I will fix that for you. But yes, in this case, it did go down. It's significantly smaller because of the addition of the slope. So, okay, questions on any of that? Section 2.
So with that one, I think I was guessing on these last two lines with the as indicated by the significant p-value of the slope. So can we explain that one more time? Because I know I want to be able to understand it for the next question too.
Yeah, what were the original choices? Let me pull that up, open up a new one and look at that. 1 second. Because I know that one was related to the intercept and one was related to the slope, and I don't remember what the other ones were. Okay. Yes, I know Google. Okay. So the choices were, I know that the change in the residual variance, it should have gone down. And I know whether or not that was significant based on a significant p-value for the intercept, non-significant p-value for the intercept, significant p-value for the slope, or non-significant. So the significant versus not is tied to the decision you made whether or not the residual variance change was significant. And which p-value that is tied to is the p-value for the slope as opposed to the intercept. And the reason for that is the earlier model had the intercept also. So the intercept stayed constant. What separated the model in section 2 is the addition of a slope for a new predictor. So if the residual variance changed, it had to be because of the addition of that new slope. More generally, this idea of one model being a subset of another, the term for that is that they are nested models. Like if you picture those like Russian dolls where you open the doll and there's another little doll inside the doll, and you open that doll and there's another little one. Like if one fits inside the other, then it's a nested model. So these are nested models in the sense that section 1 is the lowest order. It has only an intercept. In section 2, we add a slope for pleases heard. So those two models are comparable. The last model in section 3, where we add a slope for age, Section 1's empty model is nested in it, but Section 2 and Section 3 are not nested because they each have one predictor, but it's a different predictor. So they are not directly comparable. At least we haven't talked about how one might do that yet. Okay, does that help answer the question?
Yes, yes.
Okay, Section 3 then. So we talked about this at the beginning of the show, but just to recall, what does the intercept mean? The intercept is for 3-year-olds. And the reason I know that is because of the coding scheme. I told you to make a new predictor in which age 3 meant 0 and age 4 meant 1. So had I told you to flip it around, I could have told you to make age 4 the 0, and then they would have been the intercept. So it's entirely based on the coding scheme that you've adopted for who is 0 and who is 1. It usually makes more sense if you have a variable that's numeric to keep it in the same order. It would be backwards conceptually to have 4-year-olds as the reference. So then the slope estimate describes how the 4-year-olds differ from the 3-year-olds. Because the slope estimate describing the 4-year-olds is negative, they have a lower outcome, which was significant. So 4-year-olds throw fewer fits on average than 3-year-olds. And in this case, the residual variance was significantly smaller than the empty model, and we know that because of the p-value for the slope. Had the slope been non-significant, the decline in the residual variance would have been non-significant as well. Okay. Any other questions on any of these? I'm happy to go over this and make sure that we're all on the same page, because all of this material will be underneath what's coming. That is to say, this continues to build. So if you have confusion about this, I'm happy to talk about it.
Not a question per se, but I think like an idiot, I assumed that each question break was like its sole thing. So I never went back to the first one to compare the residuals to say significantly smaller or larger. I was just trying to look at my numbers and was like, oh, well, this top number is larger than all these other numbers. So
Yeah,
that was wrong.
the wording in here, than the residual variance from the empty model, that was what I had intended, is for you to go back and look at your variance, and then at least you know which way it went. And it was supposed to have gotten smaller. But didn't always, apparently. So note to self, change the starting values to make the effect bigger.
Lisa, can you, okay, I think I may have been multitasking a little too much. I apologize.
No
The,
worries.
okay, it's just the last question, or so question 68. I think I just was looking at the wrong value. Could you remind me what I'm supposed to be looking at when we're talking about the model residual variance one more time?
You mean like in the output? Or like what you would have in here?
In here. So like I think I was just comparing the wrong numbers, but I'm not 100% which numbers I should have been looking at for.
So I asked relative to the residual variance from the empty model, which was the first question. So in section 1, how much variance was there in the outcome of fits thrown, period? Right? Because there's no predictors yet. So there's that 7.71. And then after adding a predictor, it went down to 7.57 in section 2. And then after taking out that new predictor and adding in age instead, it went down to 7.13.
Okay, so we were literally comparing it to the first one. I think that's where I wasn't paying close enough attention.
Yeah, and so I tried to say that in here, in each place, like relative to the empty model, relative to what you found up above, because it's all like one contiguous set of analyses.
Okay, I think that's where I was a little off. Okay, thank you.
Thanks for asking. All right, other questions? So can I tell you a quick story about being wrong? Quick anecdote. So you're going to have to get used to the idea that whatever you put out in the world is going to be wrong at some point later as science moves forward. And that is doubly relevant anytime you're talking about quantitative methods. So when I was a postdoc, I had someone approach me with a data analysis problem, and I didn't know how to answer her question. It was about differences in variability. So I did some digging, and I found a strategy that was in a book that I thought would be useful for this. And I thought, well, maybe this could be like a little paper, because if I had to dig to find this answer, then maybe somebody else could benefit from this approach. So I wrote this little paper about it, and the reviewers wanted to make it a much bigger paper, and I said, okay, I'll add all this stuff to it. And not only was it published, but it actually won the journal's Paper of the Year award in 2007, right? So yay me. Only one problem, it's wrong. I am about 90% certain that it is wrong. I've never actually done the analysis to verify it because I really don't want to know. But I left out a critical parameter of the model that I now know is very likely to have made it wrong. And I just had somebody email me yesterday about this paper and wanting to use the model in their own work. And we looked at your code and we tried to do code to match it. And did we get it right? And I said, the good news is that you got it right. The bad news is that it's the wrong model. The bad news is that I steered you wrong. But so it's one way to look at it is, yeah, I put something out there and it's wrong. But another way to look at it is, would I really be living my best life if I hadn't learned anything new since 2005? Like, should I be proud of that? So I view it as a good thing to be wrong, because that means that you're moving forward in a new direction that hopefully will make your research better. So don't be afraid of being wrong. It's going to happen. So just casually flexing the paper of the year. Yeah, well, you know what? I needed tenure. So it was a very nice thing to be able to put on my my thing. I don't tell them it's wrong though, right? I don't have an asterisk next to the award that it's the wrong model, because don't take it away from me. But anywho, I'm wrong. I'm wrong a lot of the time. Anywho, all right. So we're good with this for now? Good for now? All right. So then heading back into extending this to look at slightly more complex models, leaving the world of simple behind and having more than one slope for a predictor. So this was example 4 that we started looking at, 3 groups. And I wanted to go back over the part that I rushed through at the end of class last time to make sure that there's everybody's good with that, because you're going to get a chance to practice this in homework 4. So your next formative assessment is available. That's due Monday of next week. Homework 4 is due the following Monday. And up to this point, we've covered the first section of it in class. I will warn you that homework 4 has historically been the most difficult in this class. It's worth 17 points because it involves a lot of new coding. So I'm going to try to give you the scaffolding as best I can to help everybody get to that point. But it is a level of complexity higher, so that's all right. We will get there. So in this case, I have 3 groups, which means I need 2 slopes. And the model directly gives me the predicted outcome for the group in which both new predictors are coded 0. And it gives me each mean difference of an alternative group relative to that reference. Anything else that's related not to the reference, like the means that the model predicts for the alternative groups, or the mean differences among the alternative groups, those are linear combinations. So in your homework, I'm going to ask you for the mean of each of the 4 groups, and I'm going to ask you, I think, 4 out of the 6 mean differences, maybe 5, I can't remember. And it will be up to you to realize which ones the model is giving to you and which ones are linear combinations. And so this is an example designed to help you get started on that process. So these estimate statements, do you want to go over these again, or do you feel good about these? So we've talked about it a couple times so far, but a couple may not be enough. What do you think?
Let's do it.
Talk over again?
Mm-hmm.
Okay. So the important thing to realize is that what these statements do is math. They are using the estimated model parameters that it found in an equation. So this line right here, intercept 1, L versus M0, L versus U0, it is doing this equation up here for you. That's what it's doing. And it's also just messed with my font for some reason. Okay, that's weird. Now it's an equation. Undo. No? All right, well, now you get fancy font with this. Who knew? So the word intercept, that refers to beta 0. So whatever beta 0 as the fixed intercept is going to become, whatever value it is, that's what it's going to take. And everybody gets a beta 0 as part of their predicted outcome, which is why there's a 1 behind it. Then the L versus M and L versus U, those words refer to whatever beta 1 is going to become and whatever beta 2 is going to become. The values in the green here behind them refer to the multiplier. What is the value of the predictor that it's the slope for? So those zeros and ones come straight out of your coding scheme. If you're talking about the middle group, that was when the first predictor that we created was coded 1. If you're talking about the upper group, that's when the second predictor that we created was coded 1 instead. And so that's why we have this patterns of 1s and 0s as such for what the model says the mean would be. So if you look at this pattern, only the last 2 are things that you would have to ask for. The first one is going to be just the model intercept, which is already given to you. But it can still be useful to label all 3 of them. That way all of your answers are in the same table. Okay, with me so far? All right, then the last ones here, the second 3. These are differences. So note that none of these differences are referring that none of them contain the word intercept, because these are differences between groups where the intercept falls out. So the math is up here. The difference of low versus mid means that I take whatever the model says the mean would be for mid, which is what I just found up here, and subtract what the model says the mean would be for low. So the beta 0s cancel and I'm left with just beta 1. Likewise for low versus upper, the beta 0s cancel and I'm left with just beta 2. So these first 2 lines are not actually linear combinations. They are already given to you directly as model parameters. Each of these is a slope for how an alternative group differs from a reference group. So how middle differs from low and how upper differs from low. So my versus is trying to help you determine who the reference group is. I'm always coding it so that the reference group is the group listed before the versus. So in mid versus upper, that's the one that you have to ask for that's a linear combination of your slopes. So we have what the model says upper is, what the model says mid is, the beta 0s again cancel, and we're left with beta 0 minus beta 1. And so that's why right here I've got a negative sign, because beta 1 has the minus in front of it. So minus is for beta 1, positive 1 is for beta 2, so it works out to be subtraction when you put them together. And the same thing is true in this data code down here. The minus 1 refers to the first variable, the 1 refers to the second. Okay, how are we doing? So then down in the output, we have our friend mean square error. That's your residual variance. So if you have that correct, you know that you have the right model. You have the right outcome and you have the right predictors. Down here in the fixed effects table is where the intercept is. If you have that correct, then you also have your predictors created correctly. So centered at the right place or the right combinations of 0s and 1s. So those are the first 2 things that I'll ask you to check to make sure that your setup is correct before continuing. Do you want to go back over this box here? Model box? Would that be helpful? Yeah, okay. So this is a summary of what you know model. So how much information was captured by your model and how many slopes did it take to get there? Sums of squares model is information captured. Number of slopes it took to get there. The 2 is right here. 2 is otherwise known as what? When I ask you for this, what am I going to ask you for?
Those are one of our degrees of freedom,
Which
and you're
one?
asking if it's numerator or denominator,
Yep.
which I'll let someone else answer. Just
They're
kidding. I'm not
numerators.
anything wrong. It's numerator, degrees of freedom, and error is denominator.
That is correct. And it's in the same order that it is in the table. The reason for that terminology, by the way, it boils down to this F. So where F comes from is this divided by this as like the top of the F, and then the bottom of the F is this divided by this. And so those intermediate divisions are shown in this mean square column. So the 14,000 whatever divided by 2 is right here. And then what you don't know is the error row. So then all the information that's left over, all the deviations of the actual y's relative to the y's predicted for them, and then how many more slopes you could have added. Then we get to mean square. And so then what you know over what you don't, that's your F right here. And F is squared, which means it will always be a positive number. So it has denominator degrees of freedom as this number right here, degrees of freedom, residual or error, that's denominator degrees of freedom. And so we need to know those 2 degrees of freedoms, the F and the residual variance and the p-value and the r-square. So that's the information that you would extract from these 2 tables that then could allow the reader to recreate all the other values if they wanted to. And you will get a chance to practice this to death. Here's your format of what that would look like. F, degrees of freedoms with the comma separating them, F value, residual variance, P value, and then R square would be tacked on somewhere in here as well. Okay. Good with all of that? Okay, then R square, that's effect size. So how much do we know in our outcome relative to how much we don't know? R square is a way of putting that into a proportion. So our R square of 0.10 means that we have captured 10% of the variability in our outcome variable. 90% is still out there. So the effect size for the model is R square goes with this F. F is the significance test, R square is the effect size. You can think of R square in 2 different ways. It is the proportion of variance accounted for by your model, as I just said, or you can think of it in terms of y hat. So if you took your original y column in your data set and you computed another column which was y hat, the predicted outcome from your model, and you correlated those 2 things, that would be R. The square of that correlation between y and y hat is R square. So F is telling you the extent to which the y hat created by your model is correlated with the real y. So those 2 things work together. So model refers to how all the fixed effects work together. Then you get your table of fixed effects, and here are the 3 betas that you asked for. The intercept, which is for the group coded 0, and then each of the slopes, which is how the alternative group compares to the 0 group as the reference. So relative to the low group, cough cough homework question, relative to the low group, the slope of 8 tells me how much more the middle group is. Middle is higher, slope is positive. Relative to the low group is the you are here reference sign. The slope of 10 tells me how much higher the upper group is. And the difference between these 2 numbers tells me how middle and upper differ from each other. More specifically, how upper differs from middle And that's the extra piece that I had to ask for down here. So this is the result of your estimate statements, the 3 means that you asked for, and the 3 mean differences. And so these 2 rows are linear combinations, beta 0 plus beta 1 and beta 0 plus beta 2. And this one right here is also a linear combination of beta 2 minus beta 1. Okay, questions on any of that? Then I threw in some pictures, again thinking about the idea of normal residuals and the extent to which that holds up in this model. Not great, not terrible. Might want to find a different way to predict income, but that's a different class. Generalized linear models. By the way, I have real numbers now. Did I tell you that? My new classes got approved. So 6270 should be your next class if you want to keep partying with me. That's the new generalized linear models. It's coming back a year from now. That would be my recommendation as to what should come next. There are other classes being offered that could potentially work. Design of experiments is coming back in the fall. That would be a good one to follow this one with as well. So if you have questions, I'm happy to help you figure out what coursework would be good for you. And then last but not least, effect sizes. So the slopes that we get out of our output here, these are unstandardized. The idea of unstandardized means that you have to know what the units are to make sense of these numbers. Like 8 what? What's 8? Well, it's $8,000 because the outcome is in $1,000 units and the predictor is a grouping variable. So 8,000 is what this slope means. I can tell from the p-value whether or not that slope is significant, but I also still need an effect size for the slope. So trying to put these 2 slopes into context, how strong of a bivariate association is there between that group contrast and my outcome, as well as for this requested group contrast and my outcome. So that's the last piece of this then that we had talked about very briefly. 2 ways to do that. One is to ask for standardized slopes. So in SAST, you need a different procedure to get this. So if I ask you for a standardized slope, that needs to come from proc-reg, which stands for regression. So proc-reg is an older procedure. It has a few things that GLM does not, which includes adjusted R-square values that are corrected for sample size, as well as this option STB, standardized beta, but it does not allow estimate statements, and it also does not allow factor variables, categorical predictors that are treated as such by the program. So it's somewhat limited, which is why I don't use it as a general rule. So I have to re-estimate the same model that predicts income from my 2 group contrasts, add this standardized slope option, and that's what generated the output below. I've highlighted in boldface the only parts of the output that are new. Everything else we got out of GLM already, with the exception of this adjusted R-square, and the very last column over here, standardized estimates. So these standardized slopes, these 0.31 and these 0.13, those are in a correlation metric. So they tell you on the same scale as a Pearson correlation, ranging from -1 to 1, how absolutely strong of an effect the relationship is between group and income. So it looks like there's a much stronger relationship distinguishing low versus middle than there is low versus upper. Now, given that one is 8 and one is 10, is it surprising that the first one is stronger? So if we just look numerically, this slope is 8.8, this slope is almost 11, yet the standardized version is much higher for the slope that's numerically smaller. Now, why might that be?
Group size?
Yeah. Check this bad boy out right here. Standard error comparison. The standard error for the slope related to the upper group is 3 times as large. The upper group only has 20 people in it out of the 734 people in this data set. Okay, am I frozen?
Dr.
It-
Hoffman,
Yeah.
everything
you did
for
freeze, but then you sped up really quickly. So after you said yeah, it froze and then everything went fast.
Of course it did. Okay, I'll try this again. So yeah, this standard error for the slope of 8 is 1/3 of the size of this standard error for the slope of 10. And the reason for that is because of differences in sample size. The upper group has only 20 people in it. So that slope is a lot noisier. Practically speaking, this slope is expected to vary a lot more across repeated samples. And so when we try to standardize that into a t-value, it's much smaller. So less precision translates into a smaller effect. So this gets you standardized slopes for model parameters, but it does not allow you to ask for standardized slopes for linear combinations. So to do that, I saved the results from the general linear model and I computed a D myself. So here's the formula to compute Cohen's D. It uses the t-value from the analysis multiplied by 2, divided by denominator degrees of freedom, 731, which is up in my table here. So that's where that number comes from. And so I computed the D's for each of the effects that I requested in the estimate statements from GLM. I asked it to print them out, and so the very last column here is what I ended up with. So D is another index of effect size. It's in a different metric. It's in standard deviation units. So for instance, my slope that would corresponded to a standardized slope up here of 0.3 in D units is 0.65. So that's telling me how many standard deviations apart those two group means are. The middle group is 0.6 standard deviations above the low group. So I can't remember if I asked for effect sizes in homework 4, but if I did, this is how you would get them. Or I may have just taken it easy on you and asked for only model parameters. We'll find out. And as always, words. Words, words, words. Okay, Fayaz, question?
Could you explain the L versus U slope interpretation one more time?
Sure. So these are the two slopes that we asked for that pertain to these new predictors that we created via dummy coding. The way that we created these predictors is that the low group has a 0 in each of the new predictors. That sets it as the reference. So then the slope talks about what happens to the one group relative to the 0 group. In this context, the one group is the middle group for the first slope. So the middle group is higher by 8.8 than the low group as the reference. Likewise, the U upper group is the one group in this comparison, and the upper group is 11 higher than the low group as the reference. And so then the difference of those two numbers tells us how upper differs from middle. That's the linear combination that you have to ask for, beta 2 minus beta 1, that I had done in an estimate statement to get that. So that's the slope difference and its standard error, which is not significant. So 8.8 and 11 are not different from each other according to this model. Okay, is that good? Good. All right. Okay, other questions on this? All right, then if not, I get to talk about something new, I think. Yeah, a whole new thing. Okay. So let me do the next model here, and then we'll segue back to the slides to talk about adding to this model. So I'm introducing a different predictor here. We're still predicting personal income in thousands of dollars. So I'm on page 7, but now I'm going to do so, I should say, via chronological age. And so in this data set, first step is to find out what age looks like. So proc means is used to provide summary information about quantitative variables. Status summarize command does the same thing. So on average, people in this sample are 42 years old. They differ. Standard deviation tells me how far off each individual is from that mean of 42, and the range is 18 years to 75 years. So I don't want to put age directly into the model as a predictor. What would happen if I did that? What if I put age directly into the model as a new predictor? Who would my intercept be for as my reference point? If I have a new model, age is a predictor of income, and I put age in directly without changing its scale, who is the reference point you are here for that model?
That'd be for just whoever the youngest person is.
Nope. If I don't do anything to age by itself,
0.
0. I would be predicting annual income for a newborn baby. Now, maybe the baby has a trust fund and actually legit has annual income, exactly, but that was not my life. So most of us, I'm guessing, we're not making money as a newborn. You can't even be in movies as a newborn. You have to be like 3 months old or something to work, which is why all of those movies where they show the newborn and it's like this chunky, 3-month-old, like, oh, that's not a newborn. Like, that is not what newborn babies look like. They look like aliens. It's not what they look like. So I had not seen a lot of newborns until I had one. I was like, oh, he looks like a frog or something. Like, what's wrong? But then he's super cute, like 3 months later. Don't worry about him. But anywho, so we don't want to put in age directly. We want to center it in some fashion. I'm going to make an arbitrary decision to say, hey, let's center it at 18. That's the minimum age in the sample. We'd be predicting annual income for an 18-year-old and then seeing what happens as age progresses. So I'm doing a little bit more descriptive information about age. I have a histogram for its distribution. And I have a plot here that I created for what the mean income is for each distinct year of age. And so to make this picture, I rounded age into the nearest 2-year interval. And the black line shows the mean, and the red line shows the standard error around the mean. So plus or minus 1 standard error. So if I look at this shape, how well do you think my linear regression model is going to capture the association between age and income? Yeah, if I try to put a line through that picture, that line's going to be flat, right? But is there a relationship between age and income according to this picture, if you just eyeball it? Yay, middle age! That's what I say. I'm rich relative to everyone else in here, making $25,000 on average. So rich, maybe not the right word, but still. There is a what I would call a quadratic or a parabolic function, or U-shaped. It looks like income increases up to a point, and at which point it kind of decreases on average, although there's a whole lot of noise at the other end of the distribution. So as people stop working as much or retire or whatnot, their income decreases as expected. So the techniques that we've learned up to this point, yeah, boomers. I'm not a boomer, by the way. I am Gen X, I think. I forget which letter is which, but whatever that. I'm not a boomer. Although the Saturday Night Live last weekend had a boomers get the vaccine video that I laughed very hard at. So I would recommend that if you have a few minutes to kill. That was a very funny sketch. But anywho. The techniques that we've learned up to this point would not allow us to model the relationship between age and income if it's in this fashion. So if I estimated a Pearson correlation, that's not going to capture the story. If I put in age by itself in a regression model, that's not going to capture the story. So let me show you what it looks like if I were to do that. So first step, center age. So I am making a new predictor here for age centered at age 18. So in my traditional way of naming these things, I tack the constant I centered with onto the end of the variable name. So age 18 is my new variable. By the way, what would happen if I did this instead?
Oh, you changed the original as opposed
Yeah.
to centered it.
I overwrite my column. So yeah, if you accidentally overwrite your column and then you realize your mistake, your original column does not have the right information in it anymore. So the solution is to rerun your code to re-import your data to get your original column back. And quit capitalizing things in Word. I would have capitalized it if I wanted to. So yes, make sure the new variable, which is before the equal sign in each of the codes, is a distinct name. The variable that you're pulling from is to the right. So I'm making a new predictor. I'm putting it in the model. So income is predicted from a linear effect of age 18. I am demonstrating estimate statements. So this is the same logic by which you predicted fits for pleases heard of 4 versus 10. So filling in predicted, filling in the value of the predictor for which you want a predicted outcome. So if I wanted to predict what the model says income would be at age 30, then I need 1 beta 0. I need the beta 1 that I'm going to ask for the slope of age, and I need to put 12 there. Why 12? The answer is right here, because I've centered it at age 18, and so to get what it would be for a 30-year-old, I need 12 more than 18. Likewise, I asked for predicted income at age 50 and predicted income at age 70. So just pick some values to use as examples here. So here's my results. So in this case, I have one predictor. So the F value right here for my model, with one predictor in it, numerator degrees of freedom 1, that F of 30.52 is the exact same thing as that t value squared. So if you have one slope, the t test statistic for that one slope squared is your model F. They're telling you the exact same information. So this is the same thing as just asking for a Pearson correlation between income and age. I'm doing it in an unstandardized slope kind of way, but it's the exact same information. So this model captures 4% of the overall variance in income. It tells me that for every year older you are than 18, your income is predicted to go up by $200 a year. So then I have the results of these predictions. At age 30, it's predicted to be $14.8 thousand. At age 50, $19,000, and so on. So it's predicting a linear relationship where as you get older and older, income increases. Now, is that realistic? Not likely. I know it's not realistic based on this picture. That's not what happens in the data. It goes up to a point and then it reverses directions. So we need another way to capture the relationship beyond just a linear effect of age. So here are some pictures describing then what the model regression line looks like through age and the residuals. So ideally, if your model is correct, your residuals should not have a pattern to them. They should be flat and even. The fact that these are heading in a not flat direction suggests the model is misspecified. We're missing something. So we're going to fix it. So let me ask you this. How many of you have seen this type of quadratic function before or worked with this in a class? Not yet? Brand new material? Yeah, that's what I figured. Believe it or not, I'm actually teaching this exact same material to my 2 o'clock class today as well. And the reason that I'm bringing it to this class is so that when you get to my 2 o'clock class, you'll know it already. The 2 o'clock class this year is a longitudinal analysis. So looking at change over time, in which change is often nonlinear. You know, people grow up to a point and then they level off, or they decline up to a point and then they level off. And so quadratic models are very common for longitudinal data, but I want you to know how to fit these sorts of trends for any kind of quantitative predictor, not just time or age. There's a lot of phenomena that a linear relationship is just not plausible for. Like, what's the relationship between money and happiness? Right? Does more money make you more happy? Well, like if you have no money, it's hard to be happy, right? If you're worried about, you know, having a roof over your head and having food and whatnot, like that sucks. But like once you have enough money to meet your needs, like does more help? Ugh. You know, research suggests there's some optimal amount, in which case more money makes it worse, perhaps. You know, more money, more problems. Thank you. Yeah, that's where I was going with that. There's a lot of phenomena where more is not necessarily better. Like the effect of more levels off. So this is one way of addressing those sorts of nonlinear relationships that I wanted to show you. I will show you the code, and then we'll talk more about quadratics more generally than next time. It couldn't be easier. So welcome to what is a special case of what's known as an interaction term. An interaction term more generally is when you multiply one predictor variable by another predictor variable. This is a special case in which it is the same predictor variable in both cases. So in some software packages, you have to physically make a new interaction variable as a stored column in your data set. One of the advantages of ProcGLM and state as regress is that you don't actually have to do that. So on the fly, so to speak, dynamically in the code, when I type age 18 and then an asterisk in the middle, that is creating this new quadratic trend. So it is a new predictor that is age squared. And when it is placed into the model in addition to the original effective age, they together create a curvilinear pattern. So this is critical. You cannot take out the original effective age. It's only quadratic if it's above and beyond the original effective age. So in this context, what we were just calling like the slope of age now is the linear slope of age, because age has two different slopes in the model. Age all by itself is a linear effective age. The slope of age all by itself would be the change in income per additional year. When paired with this squared term, it has the potential to create a parabolic curvilinear shape. It takes the linear slope and either makes it more positive as age goes on, less positive as age goes on, more negative as age goes on, or less negative as age goes on. There's only 4 kinds. So your task will be to figure out which of the 4 you actually have. In Stata code, you can do the exact same thing, but with a different symbol. This thing right here in Stata. So for those of you who are under 40, that is a hashtag. For the rest of us, that is a pound sign. So you can pick whichever. Hashtag interaction term. One of my students joked before. So it is a star asterisk in SAS and a hashtag in Stata. So that's the general idea. So this equation highlights a distinction that you'll sometimes come across in hearing what a linear model means. Do you remember that term from like a month ago or something, introducing that? What is a linear model? And the answer is any model that operates as slope times variable plus slope times variable plus slope times variable. So you will hear sometimes linear in the variables versus linear in the parameters. This is a good example of what we're talking about. Even though I have this squared term in here as a predictor, this is a linear model because it is still slope, which is beta 2 in this case, times variable. It's a linear model, which means you can use standard software to estimate it. An example of a nonlinear model would be if you have like an exponent in there or a log or something like that that disobeys this slope times variable format. So even though we are fitting a curvilinear shape to the regression line, it's still a linear model. Linear in the variables, or linear in the parameters, excuse me. But we'll save that till Tuesday, or not Tuesday, Thursday. Today was garbage day. We will save that until Thursday. So any questions before we call it a day? All right, then you should be able to do all of section 1 on homework 4 if you want to work ahead. This will be section 2, and on Thursday we'll finish this up and we'll see if we get it into the next one. So, all right, let me know if you need anything. Otherwise, take care. See you Thursday.